Okay, let's start our class today. And would you please turn in your assignments? Then who will be the first one to do the presentation today? I think this is our third assignments, right? The first time, the first presenter is Steve, right? The second one is John. Then who will be the first one of this assignment? No, you can take turn to be the first one. I think we will have 6 assignment this semester. I guess. Okay. So who will be the first one today? We like. Okay. Rachel will be the first presenters today. Then who will be the next one? Next time I really need to draw the lot to everybody. It's randomly chosen, must be fair to everybody, right? Okay, 2 more, please. Okay. Okay, so Rachel will be the first one. Then let's download it. Okay. All right. Be the bigger. Okay.
Good morning, everyone. I would like to present my assignment, and let's see about the variable first. We would like to um, like know about the consumption expenditures in the year T in billions of $2009, and the DPI is the real disposable personal income, and AAA is the real interest rate of AAA corporate bonds in year T. And for DPI, the expected sign was positive, and for AAA was negative, because the more interest rate is higher, means people tend to put the money on the investment, not on the consumption. And this is the consumption function. I got this result from eFuse, and this is the equation. And examine the residuals from year T on the x-axis, and I got this plot. Like, as you can see, the plot like the zigzag one, so the plot doesn't seem random. However, it shows positive serial correlations, because the error terms tend to have the same sign as the previous observation in the error terms. And for the Durbin-Watson test, for the null hypothesis, if rho is less than 0, it means no positive serial correlations. And for the alternative hypothesis, if rho greater than 0, it have positive serial correlations. And the appropriate rules is, if D is less than 1.49, that means reject the null hypothesis. But if D is higher than 1.69, it's do not reject null hypothesis. But if D is in the between of 1.49 and 1.69, it means inconclusive. And for the upper and lower critical value in this case was because the number of the observation is 62 with 2 explanatory variables and 1 coefficient with 5 level of significance, the upper critical value is 1.69 and the lower critical value is 1.49. And this is the Durbin-Watson statistic.
K equal to 2, right?
Yep.
Then what's the sample size here? Let me
62.
62. Okay, so N is 62. So what's the lower and those critical values?
1.49.
1.49 and 1. Where did you get these numbers?
Oh, isn't it the explanatory variable plus 1 coefficient as the K?
So K equal to 2, right?
Oh, So just the two variables, not plus one coefficient.
Here, K means number of, N is number of observation. K is number of explanatory variable excluding the constant. So K equal to 2, right?
Oh, okay. So it is one.
So K equal to
point
2. So the critical value is
1.45.
N is, say it again, N is equal to
62.
62. N is number of observation.
Yes.
So 62 we can check with 60.
Uh-huh.
And so the range is 1.51, 1.65.
Oh, okay. So
Is that right? Is that right?
Yeah, so I was wrong.
Okay, K equal to 2.
Yeah. I thought because the K is explanatory plus
Minus the
Yeah.
constant, right?
Yeah.
But no, here means K. Usually, in this book, maybe you check with the other book. I don't know, but in this book, constants always start with 0. So X is the first one is denoted by X1, etc. Okay, if you have two variables, so this is two variables.
Just to, okay.
Okay, so K equal to 2.
All right.
And check with the number of observations, so 62, all right? So it's close to 60. Therefore, we can use 151 and 165. Maybe, it won't hurt your result, but the number is wrong, okay? Okay.
Okay, thank you, Professor. Okay,
So you're running with Durbin-Watson statistics,
yeah,
right?
this one.
Check with, yeah, okay.
Yep. So the result is 0.38,
Mhm.
and it's less than 1.49. But this number is wrong. But
yeah, but
the
actually it's
but
still
actually
smaller.
it's still smaller. Yeah.
Yeah.
So
okay.
the result is rejected the null hypothesis. There is the positive serial correlation.
Mhm.
And for the Lagrange multiplier.
Well, did I show you that? I forgot. Do I show the Gretel?
Yeah.
It's about the Durbin-Watson, right?
Yeah.
And they do have
The
the
p-value.
p-value.
Yeah.
Yeah. Okay.
Yeah.
But this is called critical value approach.
Yeah.
Okay. But either way is okay. All right.
All right.
So I just like to mention this one. Okay. All right. Number.
And for step 5, for the LM test, are the null and alternative hypothesis for LM test as the same for Durbin-Watson test? And usually they are different.
Mm-hmm.
For the LM test, the null hypothesis is that there is no serial correlation in residual.
Mm-hmm.
And for the Durbin-Watson test, the null hypothesis that is no first order autocorrelations in residuals. Like for the LM test, they can have in if the leg is more than one. But
Yeah, sure.
for the
Mhm.
Durbin-Watson test, just for the first order only.
Mm-hmm.
And this is the result for the LM test.
And yeah, I like to mention a little bit about this one. Actually, from our textbook, they are using observation times R. So it's the second one in our textbook, right?
Yeah, this one.
Yeah, but actually, both of them is okay. Yeah, it can be done two ways, okay? And from our textbook, they already show the numbers, which has a chi-square distribution. Yeah, okay.
Okay, for LM test, Army would like to explain the
Chi-square. Yeah,
Chi-square.
chi-square. Okay. chi-square, not chi-square, okay? It's chi-square.
But chi-square is smaller than alpha level, means rejected null hypothesis, and this is the result.
Well,
0.000.
I like to say that
Uh-huh.
0.000, this is not chi-square.
Mhm.
This is what?
Oh, p-value.
The p-value of the
Chi-square.
test statistic, okay, which is chi-square distribution. The test statistic is this one. This is what we say, 39.91.
The
This is
observed.
test statistic, okay? And the p-value is the probability, the tail area of the test statistic, okay? So this test statistic distributed as a chi-square distribution. So if you say chi-square, then, it's not clear. It's not clear because chi-square is a distribution. How can you have 0.000 something? Okay, so you have to say p-value of the test statistic.
Okay. Okay, so this one was p-value of the test of the statistic is 0.000 and really close to 0, means smaller than 0.05, and means there is a positive serial correlations.
Well, since this is LM test, so it is two-sided. So the conclusion will be there is serial correlation.
Ah.
Two-sided, right? But we know that this is positive.
Okay.
But actually the conclusion says there is serial correlation existed.
Oh, either it is positive or negative.
Yeah.
We just should say there is serial correlation.
That's right.
All right.
So that's the difference between Durbin-Watson and the LM test.
Okay.
Remember that?
Okay.
One, you already mentioned one
Yeah.
is one-sided. This is two-sided.
All right.
Okay?
That's right. Okay.
Okay? All right. Very good.
And for the Q statistic test,
Mhm.
I got this number, and the Q statistic here, the number is the same as the LM test above, and the probability of the statistic test was
Yeah.
0.000.
Is this number exactly the same as the LM or somewhat different? What's the LM numbers? 39.91 something. And Q is 38.89 something because the logic behind is similar, but they are using different formulas. There's a little bit difference
Of the
about their
decimal,
numbers.
yep.
Okay. And Dylan, this is I remember 2 or 3 weeks ago, you asked me about this one. Then I say that we'll mention this one later on. So this is where we will talk about. This is serial correlation. All right? Okay. All right. And since this is just one leg, therefore, what you see is just one. But actually, if we have the more legs, we will continue to talk about this one later on, okay? And usually we do have more than one, and you can see the whole lots of Q statistic here, okay?
Okay.
All right, thank you.
All right, and this is the GLS test. No, the test, the estimate model. I re-estimate using the AR1 here.
Yeah, this is using in EViews.
Yep.
Okay, just add one more, which is called the first autocorrelate. AR1.
Uh-huh.
Okay, AR means what? Autoregressive.
Autoregressive.
Then, I will talk about this later on. Okay, but you put this one here means, the program. This is really by EViews program. Okay, if you're using EViews program, you add one more, which is called AR1. Then it turned out to be what we say generalized least square, and which is what we call in this textbook is, usually I don't remember this name. They say Price-Winston methods. This is what we say in the book. Price-Winston methods. There are several methods of the general least squares, okay? And this is one of them. And the authors say that, maybe the popular one is not this one, but our recommendation is to use slightly different approach, and it is called Price-Winston methods. And fortunately, the EViews, the programming, when they do the program, they're using these methods. And they ask us to add one more term, which is AR1, then it will turn out to be the result of these methods. Okay? All right? Go on.
All right. So this is the comparison between the original one and the AR1.
Mm-hmm.
And as you can see, the how to say, the slope coefficients, some of them are increased and some of them are decreasing, but because different estimate can have different value of expected value are the same, it's the same with the t statistics. Some are decreasing and some are increasing,
Mm-hmm.
like as you can see from this one.
Okay.
And in the original one, I used the Durbin-Watson here, and for the auto regression one, I use the row sign here as this one.
Well, there's a new Durbin-Watson statistic here, right?
Yep.
Yeah.
And yeah. And after the GLS transformation, does the serial correlation still appear to exist? And after GLS correction, I test the regression with the LM test again and get the result here.
What do you, excuse me, let me see what. After the GLS transformation, oh, this is the question.
Yeah,
okay?
this is the question again.
Okay.
The C question.
Then I test the regression with LM test, the result of LM test, okay, and get the okay.
Yeah, so I do the LM test with the GLS result.
Mm-hmm.
So I got this number, and the probability of the test
Yes.
is 0.392, and it's greater than 0.05. So do not reject null hypothesis, means there is no serial correlations. Oh, this one I put it.
No. Do not reject null hypothesis means what?
There is no serial.
No. There is not enough
there is not enough evidence to
infer
the alternative
serial
hypothesis.
correlations.
All right.
You cannot say no serial correlations.
There is no enough evidence to infer there is a
Serial
serial
correlation.
correlations. All right.
Okay, very important. The conclusion is very important. Okay, we're not proof no serial correlations. We just prove there's no serial. No, we don't have enough evidence to show there exist serial correlations. Okay.
All right.
All right. Is that interesting, or is that, really,
Yeah,
is it reasonable? Makes sense. Okay. Okay.
but sometimes we forget.
Yeah. Okay. Okay.
All right. And for the step 7, calculate the new West standard errors. Um, so I ran the new West method with a lag of 1, and I got this result.
Mm-hmm.
And this is the comparison between the new West and the original one. As we could see, the coefficient is exactly the same,
Mm-hmm.
and the standard error are, some of them are increased and some of them are decreasing. And for the t statistic, it's decreasing. And why are the new test statistic different from the OLST statistic? Um, Actually, I'm not really sure about this one, but I'm trying to say that the new T statistic can be different because um, the new methods accounts for this serial correlation by adjusting the standard error of the regression coefficient, while the OLS methods assume that the residuals are uncorrelated. That's why it makes sense to adjust the estimated equation in the way that change standard error but not the coefficients. And practically the new US models are preferred because they could provide more accurate standard error and lead more reliable hypothesis tests. Okay.
I think the explanation is pretty close to the the idea of who did this one. What's the who proposed these methods?
The new US
Do you yeah? Do you know?
is
Actually, is the same idea about us. Do we use this kind of methods before?
is it the white
White test in what area?
in the wait, I forgot, heteroscedasticity.
Huh? Hetero. Oh, okay. Yeah. In the heteroscedasticity problems, right? Okay, White suggests or propose that since OLS still has unbiased unbiased estimator about the coefficient, so we don't have to change the value of the estimator of the correlations. But the standard error is different, just like you say that they assumes there's no zero correlations. But we do have zero correlations. So they adjust the standard error in order to make the standard error more accurate. Okay? Then we can trust all the hypothesis testing, the result of hypothesis testing. Okay? All right, good. Thank you very much. So what will be the next one? What will be the next one? Nobody? Rachel, who will be the next one? Oh, John. Very good. John will be the next one. Then the next one will be the Steve. Okay, let's take turn to this two-sided. Okay, business students engineering. Okay, so John. Okay. Sure, sure, sure. You know, this is I have I have taught in this university for 27 years, and I haven't any experience with the students. You know, have we have this business students, also engineering students, sitting in the same room and talking about the same topic. It really is the first time for me. You know, I have taught 27 years old. Okay, so I really excited for this course, since we have this, you know, interaction with the business students and engineering, which is wonderful. Although, you know, we have very small size, but maybe it's, you know, the small size is good to all of us. Okay, so I really enjoy this, huh? Small sample size, then, and you know, we can do some explanation either from the theory sides or from the practical sides. Okay, and you know, really understand the thinking about the engineering students and the business students, and different style of presentation of the business students and also engineering. So I'm really excited. I like this course. I never had this experience before. You know, at the beginning when you three enrolled this class, I really worry what, you know, what topic I can give it to the engineering students. I never thought about that. Okay, so you really inspire me, you know, in my in my teaching. Okay, so I really hope what I do, this semester, the material will really help you. Okay, also help with the business students. Okay, this topic is usually, you know, I talk for business students only, but not engineering. Okay, okay, all right.
Okay, so good morning, Professor. This would be my assignment. So for the step one, I also did some analysis or initial analysis regarding the dataset. So as we can see here, there is somehow of a perfect correlation or perfect relationship between consumption and DPI. Also, there is a visible relationship between year and consumption together with the DPI. So this is further backed up by this correlation heat map. However, Professor, the correlation for DPI and consumption is not really 1, but really close to 1, like 0.99 and something. Consumption with DPI, the correlation coefficient, Professor.
Oh, really? It's
really
pretty close to 1.
It's really close to 1, like 0.99
Okay, all right.
and other numbers. So this is the OLS regression result for the data set. So the R squared is 0.99 and the
That's really small.
yes.
Can you make it larger? No, this is just only 70. Make it 130. My eyesight is really not good.
Oops, yeah, there.
Okay, all right.
So
OLS,
yes.
the result. This is OLS result.
Yes, Professor.
So here. Okay. Okay, this is confidence interval. Okay,
Yes.
here. Is it the same as yours, Rachel? Is this OLS is the same as yours? Would you please check it? Is this the same? Yeah. Okay. All right.
So given the assumptions of the signs in step 1, the GPI is positive and the AAA is negative. So this is the plot for the residuals with in
Years.
years in X and residuals
Oh,
in
okay.
E. So we can see somehow of a trend here, Professor,
Yeah.
that goes somewhat of sine wave. Yeah, sine wave.
You know, this is really positive zero correlations,
Professor.
right? From the first one, it's really up, 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 then up to some point, down, down, down,
Then up.
then up, up. So really positive zero correlations, okay?
So, assuming that I don't know the term for serial correlation yet, Professor, this plot suggests the presence of autocorrelation based on residuals, and it means that the residuals are not independently distributed over time. So, for the Durbin-Watson test,
Mhm.
these are my hypothesis. Then, the
Now
Durbin-Watson.
hypothesis what? Greater than 2.
Yes, Professor.
Then what is A? Alpha.
Alpha.
What
Or
is the alpha?
the test statistic value, Professor. Huh? Oh, yeah.
Oh,
Huh?
okay.
Yeah.
Usually, in I think we don't use alpha. Alpha usually in statistics is a level of significance. So, do not use alpha as the to stand for something else. I
Okay,
think it's confusing.
Okay, Professor.
Okay, so for the Durbin-Watson, we usually use D. D.
Okay, Professor.
Okay,
Noted.
and let me see. Did you see this? Okay, okay. The test statistic for Durbin-Watson. This is what we say. This is stand for D. D. Okay, but you do the hypothesis testing. It's not D.
Okay.
You have to use rho.
Okay, Professor. Noted.
Okay, so look at the book for positive zero correlation is rho greater than 0. So instead of greater than 2 or something.
Okay, Professor. Then,
Excuse me, would you please lower down? Is this how you express in engineering? Run the Durbin-Watson test, the null hypothesis is something greater than 2?
I just searched that.
Oh, you did it by yourself? Okay.
I just researched the possible interpretations for the Durbin-Watson. It's not the standard.
Okay. You know, in the business area, if we do this one, we have the standard form or notations. But statistics usually, alpha, you never stand for anything else except level of significance. So because I think this is universal notations, okay? Not just in Taiwan or in somewhere else. If you look at papers, they are using alpha as a level of significance. So do not use the alpha here.
Noted,
And
Professor.
here we use the rho. Rho is something like this one, like P, but look at since it is the Greek letters, so something like this one.
Okay.
Okay,
Noted,
so
Professor.
put rho, and it will be for Durbin-Watson is greater than 0. So this null hypothesis will be less than 0.
Okay.
Okay, all right.
Thank you, Professor. But in my upper and lower critical value, Professor, I'm confused somehow here, because the one that I got, the lower critical value is greater than the upper critical value, which is
How come your upper and lower is like these numbers? If I check with our tables, although I don't have the exactly number, it should be 1 point. I don't forgot. If you check with the computers, usually computer have exactly. If you can check with, like since our observation is 62.
Okay, Professor. But I researched on this and what possible explanation I might have for this. So it has been said that if the upper critical value is less than the lower critical value, this indicates evidence of positive serial correlation in the residuals.
Wait. If the upper critical value is less than the lower critical value, what do you mean by that?
Upper is less
Upper is usually small, is greater than lower.
Yes,
It's-
Professor. That's why I researched on how could I possibly interpret this one. So this was the result that I had from reading some materials, but I'm still not sure.
What did you check?
What's the meaning if the upper
Oh,
critical
your
value?
upper. Okay, the one you find it upper is
Lower.
smaller
Yes.
than the lower critical value. Then something wrong with your upper and lower critical value.
That's my initial assumption, Professor. But since I used the predetermined function and I used a formula from that function, I get the same results. That's why I'm really confused between this one.
Oh, okay, okay,
So maybe
okay. Maybe I don't know what's
I
wrong
will use
with.
EViews next. I will not use Python.
Well, the programming is wrong, I think.
Yeah.
Which one is textbook? From textbook?
Yeah, I will use it EViews next time to verify my answers. So I think this one is wrong. Then for the LM test, Professor, these are the values that I had. So my LM statistic is 37.55. Then my p-value for the LM test is
Very small.
very
yeah.
low. Yes. Then my F statistic is 10.65. Then very low p-value for
Is
the
this the same as yours, Rachel? Is the L? Well, never mind. I mean the F statistic. Did you please check your F statistic? And F statistic. This is Lagrange multiplier test is another test. Okay, the one we're using. Let me see. Do we call it Lagrange multiplier test? Oh yeah,
Yes,
okay.
sir.
But we do use, what's the terms of it? We use number of observations times R square.
Oh.
Okay, that's our LM. Is this LM numbers as yours? A little bit difference, right? Your has 38 something, right? 39 something. So where did you get these numbers?
On the stat models API, the pre-built function from Python, Professor.
Previous function.
Yes, not
Well-
my function, but the Python function, Professor.
So you use some others program.
It's some like a library, Professor, that I could use for statistics.
Okay. Okay. Well, so I don't know. Then how about the F? It's different. So I think this is wrong.
Okay, Professor.
Okay. Okay. All right.
Then, for the GLS, Professor,
Yes.
I had the same results with the OLS.
Oh, that's wrong.
Yeah. And I also tried other methods for doing the GLS, but still the same results. So for calculating the Newey West estimators, these are the results that I had, and
This is Newey West, right?
Newey West, Professor. Yes,
And,
with lag 1.
This is the standard error. Rachel, did you see that? Is this the same as yours? Is the estimation? I mean the coefficient is the same. It should be same as OLS, right? It should be matched. Look
Yes.
at your result with newly. So all different. The coefficient is different either, and the standard error is different. Yeah, the same as OLS.
No, I think that one is the one.
Huh?
That's the thing. The 23.09. That's and
2309.
and the point.
.004. What is the point?
That's oh yeah, that's the one.
Where did you get this one? Standard arrow.
From the covariance matrix of the New West.
What do you mean by O standard arrow?
The original.
So it means OLS.
Yes.
But we have several standard arrows for each one of them. It's really confused me. Huh? Can I see your New West result? To make it larger, I really, it's hard to see. So really different.
No, you see
The
that.
standard, you see the adjusted standard error on the below part is 41.45 something.
Adjusted. Which one is 41?
This one, the standard error.
We have three standard arrows. One for intercept, one for.
The first one is the constant, and the second one for the DPI.
Let me see. I didn't see. The second one, standard arrow, where is it? 4.72. Where is it?
No. There's no 4.72, but there is the DPI. Right.
Yeah, just DPI and the constant.
The result of the standard arrow. What is this? What is this?
These are estimator values, Professor, but this was just for lab 1, but I forgot to delete this one. But this is
Oh, really? Oh, it's really confusing. Well, this is not. Okay. So the GLS is New West, right? This is called New West. Then anything else?
that's
That's it. Okay. There's a lot to have to change it. Yeah, okay. Okay, thank you. Then Steve. Or let's go on. Here, yeah, this one. Download it and turn it on. Okay.
Okay. So the step 1, the expected sign is positive for the disposable personal income, which is basically income, and the second one is the real interest rate for corporate AAA corporate bonds, which is negative. And here the reason is that actually this is wrong. Here should be negative interest.
Huh?
Should not be a reciprocal.
What is that? Alpha equal to interest.
No.
What do you mean alpha?
No. This means have a positive root.
Consumption alpha.
Yeah.
What do you mean consumption alpha?
Like what
And why don't you have intercept in the model? You should have intercept in the model. There's no intercept in your model. I mean this one. You should have intercept beta 0 plus this one. Beta 0. For Durbin-Watson statistics test, the model should have intercept. And usually we do have intercept. Okay. Better 0.
Oh,
Well, you don't have to,
like this?
yeah. This is the correct model, okay? Then what did you write it here?
Oh,
What is this? Consumption.
oh, this means direct proportion.
Huh?
Direct proportion. Direct ratio.
Oh. Consumption, then this is
Yeah.
this one, right? Do you mean this one?
Oh,
You mean this one? Means what?
is that here?
Very similar, or very close. Instead of alpha, then you should use the correct notations. Instead of this, or use words instead of notations.
And so it's the direct proportional for between consumption and income is because you earn more, then usually you will spend more. And the reason that is negative negative relationship with consumption, because if the interest rate is high, usually you will want to save money instead of spending money.
Well, in the future, if you give the report or result to any, to the professors or your assignments, never do this one, okay?
Okay.
Okay? Do not do this one. Really confusing.
You mean don't explain the?
No. I mean, use this kind of expression.
Oh, you mean this?
You
one?
mean this one? I mean this one.
Okay.
This one, okay? Using words is better than this, right?
Okay.
Okay? Especially, if your thesis.
And the second step, this is the result. Hello.
Okay.
This is
Yeah,
the
you have to use this one in order we do the recording.
Okay. This is the result for the step 2. And as you can see here, the probability part,
Mm-hmm.
it's all lower than 5%.
Yeah, okay.
Although it's one-sided, it's still lower than 5%. So therefore,
Officially, the expression like this one is not right.
you mean
You mean
rogue?
this is a probability of you. If you want to, officially say write down something, for this one, you have to say
Divided by
probability of any one of them.
oh, t-test.
Yeah.
You mean I need to change it to that number?
Yes.
Oh.
Then less than what? The probability is
Uh,
then less than alpha.
okay. Okay.
Okay? You really have to polish all the writings or reports.
Okay.
Especially, if you're working on your thesis.
Okay.
Okay? Now this is just, class assignments. So I may just neglect about this, but I have to correct you. Okay? If I don't correct you, you thought this is the right things to express the idea or your result, but actually it is wrong.
But can I write like here, like t equals to
No.
191.
T,
So it should be
no. T, okay. And you should identify which ones, T1 or T2, right?
so
Okay, since the first one is DP, this is talking about DPI, right? So it's T1.
Okay.
Okay, from your model, that is the X1, then which is T1.
So should I write like this
Then
for next time?
less than which is the positive sign or negative? Expected is positive or positive. So greater than
Okay.
probability of T greater than
Greater than
these numbers.
this.
Yes. Greater than that number. This is not on the subscript. Yeah. Equal to no, outside the parenthesis, equal to 0, less than alpha, less than alpha. Alpha is 0.05. Actually, this is pretty close to 0 because it's too big.
So if the next one for AAA, I should
Yeah,
write
same
equal,
thing,
equal
same
to.
thing.
Okay.
Okay, this is the officially, and the P here, since it is all equation, so the P have to be inside the equation. Should be, this is you should write down this as an equation form instead of a word form.
Oh, okay.
Understand what I'm saying here?
This
You
one.
have to use the equation form.
Okay.
Okay, you don't have to change it right now, but later on, if you write down official report, you should do that way.
Okay.
But if you can do that, from all these assignments, then you'll get you'll set up your habits
Okay.
to write down the right thing, right?
Okay. Thank you.
Okay.
Oh, and the third one, so the result is, DPI and AAA are both rejected the null hypothesis.
So you don't have conclusion. It just reject the null hypothesis, and what's the conclusion?
Which means these two are important enough to.
It's positive, then one is negative, right?
Oh yeah. To
So-
influence.
So you should write down the conclusion instead of just reject or you have no conclusions.
Oh, okay. So you mean the conclusion just right? DPI positive and AA negative.
Yeah, one is positive, one is negative. Since we're testing
Okay.
the positive and alternate and negative relationship with all these variables, with consumption, right?
Okay.
Okay.
And so the next one, general residuals from regression in step 2, and plot them as a line graph here. This one.
What do you mean by year?
Oh,
What's the year on the top? What does that mean?
is
E as residual with the variables, right?
I think it's a.
What do you mean? VS variable means residual with variables.
Yeah.
And what is the year mean?
I think is not quite sure.
Okay, and what's the second one? What's the C here? Consumption?
Yes.
Huh?
No. It's a
What's this?
constant here.
Why do you have to draw the diagram like this?
I think I do it wrong.
What all this diagram shows? And what's the information? What kind of information we need for this intercept and years?
I think I do the wrong plot, but the number is really close to what they have. So
What do you mean that number? What kind of number? Close to one.
the number like here, the range here. Well, for this part,
Well, I don't think we need to draw this diagram.
okay.
And this is relation or the information we don't, is not provide any information here. Okay.
Okay.
All right, go on, go on.
Okay. And according to the textbook, the plot looks like a positive serial correlation.
You're the one we just showed, John just showed.
Yeah,
It's really positive correlations.
Yeah.
That diagram is good.
Oh.
Okay. All right.
And the
Go
step
on.
4,
Mhm.
conduct a Durbin-Watson test,
Mm-hmm.
and the null hypothesis is rho less than or equal to 0, and the alternative hypothesis is like this. And the result here, the number is
Mhm.
0.3857,
Mm-hmm.
which k equals to 2.
Mhm.
I thought is including the constant variable, so that's why I write 3.
Oh, okay.
Yeah, but it should be 2 here. And so according to here, this diagram, it's less than 1.51. The Durbin-Watson result is less than 1.51, which is lower than
Okay.
the lower limit, which reject null hypothesis.
Mm-hmm.
And even from the output from Gretel's, the p-value is very small, which
Mhm.
is highly likely
Okay.
to be 0.00 something. So even the p-value here is smaller than 5%. So overall, consumption function has a positive. Well, it's not positive here. Just there's a serial correlation. But from the graph, we can tell it's a positive.
Well, from Durbin-Watson is positive, right? Positive.
Okay.
Look back your non-alternative hypothesis.
So if it's higher.
Look at your
higher than-
non-alternative hypothesis. Look back your non-alternative hypothesis. Look
Yeah.
at what you say. The alternative hypothesis is positive,
it's a
right?
positive. Okay.
So actually, the result here is positive serial correlation.
Okay.
Okay.
So step 5. Run a LM serial correlation, and the first one is have to compare the null hypothesis between
Mhm.
LM test and Durbin-Watson. So this is the
What do you mean by
A3.
is this
You mean this
a
one?
third?
Oh, this one is actually by textbook. It says the last the coefficient of the last variable,
Mm-hmm.
which is 3
We
in
can-
this case.
Yeah, but although we have we have two variables, okay, but you didn't write on the models,
Oh, you mean
which
here it
is
should
the
be 2?
alpha 3, and do not use alpha, but especially, but
Oh,
but-
yeah,
but
textbook
I
is-
know here if you say alpha 1, alpha 2, maybe it's okay, but not just use alpha, okay?
Okay.
All right, so this alpha is okay, but if I were you, I would never use alpha to stand for anything else.
Okay.
Okay, so actually we're using beta as our correlations, coefficients. Okay, is alpha. So here is looking at is there any serial correlations. So according to our model, the textbook, our model, using the Lagrange multiplier test, right?
Mm-hmm.
Okay, let me see. Lagrange multiplier test, and actually they're writing right on the, let me see, Lagrange multiplier test. Lagrange. They're writing the equations. Therefore, using residual as in y variables. So you have to, after you have to write down the equation like the textbook, then you can say the alpha 3 or alpha something.
Okay. Okay.
Okay?
Okay.
Okay, you cannot just use this one.
Okay.
All right?
Also,
Or we can just write down that Lagrange multipliers test. Actually, since we're working with the serial correlation problems, and the book just showed that actually we are looking at the AR1 from the EViews output, right? So according to that result, which is the third variables, except our two original x variables. Okay, so you have to write down the model first in order to write down the notations for Lagrange multiplier test. Otherwise, you just use words to do the expression.
okay.
That'll be fine. Okay?
Okay.
All right?
You mean here I can write in words, or just
Yeah. Since we are using, we are test the serial correlation. There are two methods. One is called Durbin-Watson. The other one is Lagrange multiplier test.
Okay.
Okay, then we do have the output is LM test the statistic, right? Which is 38 or 39 something. And the probability of that 39 something, okay, the chi-square less than 39 something is equal to what? It's very small, 0.0, close to 0.
Okay.
So the same expression is like I just told before, okay?
Okay. Also, it's not the same, and the LM test output is based on the chi-square. So, the part B, conduct a LM test at
Yes.
5%.
Yeah.
The result is here,
Yeah.
very close to 0.
Mm-hmm.
Oh, yeah, here should be changed. Since here should be the probability of
Chi-square.
yeah,
Yeah.
wait,
Okay.
yeah.
Alright.
The hypothesis, new hypothesis rejected, so correlation exists. So that's another way to prove that the serial correlation.
Yeah. So
exists.
actually, is reject the null hypothesis. Excuse me. Say that
Where?
conclusion.
Here.
So this one, null hypothesis rejected, right?
Yes.
So there's enough evidence to
To-
show the alternative. Then what is alternative? Serial correlation exists. So it's not just only correlation.
Oh,
It's serial correlation.
okay.
Okay?
Step 6, GOS.
Mhm.
The left-hand side one, this is the original one. here.
Yeah.
And the right-hand side one, this is the one after adding AR.
AR1.
Yes. And as
It's
you can
Price
see.
Winston methods in our textbook.
Oh, okay. Yes. So the Durbin-Watson test here from originally 0.38 to here 2.07.
Yeah, usually if you look at Durbin-Watson statistic close to 2, usually there is no serial correlation exist.
Mm.
Okay, so Durbin-Watson
But there's
statistics, just remember there's this is just rule of thumb. You have 2 for Durbin-Watson statistics. If it is pretty close to 2, then there's a lot of probability that there's no serial correlation exists.
There's no way to prove no serial correlation, right?
Huh?
Is there a way to prove there is no serial correlation?
Yeah, we do. But
We
I mean,
haven't-
you can check with the p-values, or you can check with the critical values. Actually, That's the official test. But I mean that if you don't have anything on hands, then just look at numbers.
Oh, okay.
That's rule of thumb. I just say it,
Okay.
right? It's a rule of thumb. If you look at 2, then you know there is no zero correlation exist. They do have the test, official test.
Okay.
All right?
So the coefficient and the t-statistic the same. No, for variable DPI is similar, as you can see here, the coefficient here, and here is both 0.93, but the rest is a little bit different. And for AAA it's just different. Here it's just negative 12 and
I mean,
negative 4.
okay, this is GLS, right?
Yes.
Okay, all right.
And the result is slightly different because GOS has
Mhm.
an extra variable AR, which fixed the serial correlation problem in.
Yes.
Yeah.
But it is still significant.
Yeah.
For DPI and AA, all significant.
Oh, yes, yes. But
There's no change for the result. I mean, the conclusions is all significant.
yes.
So what do let me see. The result is slightly different. What do you mean by slightly different?
Oh, just by the numbers.
Okay, just by the numbers.
yeah,
Okay,
you see the
okay. But the
coefficient.
conclusion is the same.
Yes, yes.
Okay, all right.
And the third one, after GLS transformation, the serial correlation still appear to exist. So as we can see from the LM test
Mm-hmm.
with the ARMA variable, with the ARM variable. Now,
What is this?
LM test.
LM test.
Yeah.
Okay.
And you can see the chi-square here.
Okay.
Is not smaller than 5% anymore. It's actually greater than 5%.
Yes.
So, which do not reject the new hypothesis. That means the serial correlation don't exist after using GLS method. Okay. And the seventh step, if you ran into a GLS model in step 6, now estimate the aggregate consumption by using New West. So the left hand side still the original one, and the right hand side is the new one with New West method. As you can see, the coefficient here, it's the same. However, the standard error increase, and the probability is almost the same. So I think the biggest change is standard error increase a little bit.
Okay.
So here just asking the coefficient,
Mm-hmm.
and this one is asking the statistic.
Mm-hmm.
So it says which do you prefer? I think is not quite sure what this question asking, but probably asking the method
Yeah.
between GLS and New West, right?
Between, okay, let me see. It's E parts, right? What does the question say?
What are they?
Why
the-
are New West different from OLS? So the comparison with the New West and OLS.
Well, definitely New West
Yeah.
then. Yeah.
Yeah, okay. All right. Thank you. So what will be the next one? So you're using, okay, all right. Okay. So after you connect that one, ours, they change to yours. Okay, okay, sure.
Hello. So this will be my assignment, Professor. So I'm using a lot of libraries. So don't worry about that.
Well. Assignment number 3, we are talking about serial
Oh,
correlation instead of
serial-
multicollinearity.
Not yet. Okay. Oh, sorry. Yeah. So serial correlation, Professor. So
Okay.
these are just the libraries I used. So
Okay.
many, but I didn't use all of them though. So I just got the data from Excel. So I
Mhm.
converted it here.
Okay, sure.
So just the usual there.
Mhm.
And I immediately used OLS to check the predictions here. Okay. So the coefficients are just the same as the one in the hypothesis.
Mhm.
And so yeah, there. So I did a bit of the model here, Professor. This is how would I would
Mhm.
express it.
This is engineering students show the matrix.
Yeah, since I would like
Business students
Oh, yes,
s-
just this.
seldom look at that way because we don't have math trainings. This is called linear algebra.
Yes.
If you want to understand this one, you have to take some courses about linear algebra.
Yeah, so I prefer showing this.
Yeah,
since-
sure, no
Because
problem.
the constants, I can easily paste the constants here.
Yeah,
and just
okay.
the variables on the other side.
Okay?
So yeah. The next thing I did is try to check for the autocorrelation here. So I did not compute the value, Professor, but rather I plot it, but still don't understand much.
Well, so this is your autocorrelation function.
Yes, Professor.
Okay, so how many legs do you use?
Only one, Professor. One lag for this.
One leg show autocorrelation.
Oh, this for this one is 1 to the size of the size of the
60.
Yeah, Professor. So 1 to 60.
Our observation is 62, I think.
Yeah, I think
So
it's around 60.
this is 62 legs.
Yes, Professor.
Okay.
So one progression to 1 to 60.
Yeah. Okay. If you just put one leg, you shouldn't have these functions.
Oh, sorry.
You should,
That's
should
all.
have. You should put as many as legs.
Mhm.
Usually we do legs. For autocorrelations, we can use up to the number of the
total.
sample size.
Yeah.
But sometimes, especially I don't know why engineering in business, maybe we have 10,000 observations. So I'm not able to use that many legs to show the autocorrelations. So we'll choose
Very.
like one quarter or something. Even if I have 10,000, then one quarter will be 2,500. It's still big. Okay, so usually it was if it's really by experience, if they know the patterns or something, maybe choose 5 years or so, which is will be 60 lakh, or 3 years is 36 lakhs.
Yes, Professor.
By usually we have year by years data.
But usually, Professor, in engineering, we don't know the pattern yet. So
Mhm.
that's why we tend to plot
Use
everything.
the old observations.
Yeah,
Okay.
and see where we need to cut.
Right. And look at this diagram. It's really, zero correlation.
Mhm.
Yeah. Okay.
Also
Eh,
with the
look at. Excuse me. look at their diagram, okay? Which is really helpful. Okay, good.
So this is for the autocorrelation. This is for partial autocorrelation.
Yeah?
So there also shows that, yeah, there is still in the balance.
Okay,
Yeah.
we'll get to this one too. I haven't done this one
Yes.
yet. Okay? We'll get to this, okay?
Next
Sure.
is step 3 is plotting the residual plots versus the year. So we can see
This
here-
is the one you draw, right? Residual with the year. How come? Why do you want to draw the residual with the year?
because the assignment said so, Professor.
Oh,
That's step 3.
do we?
Yeah.
Okay, let me see. Which one?
Step number 3, I guess, Professor.
What questions? Which step?
Number 3, Professor.
Number 3, generate residual from the regression in step 2 and plot them as a line graph against the years. Okay?
Lines, I didn't-
That's the plot. So you're doing the right thing.
Yeah, no, I don't understand why it's
Okay? Okay, this is by year. Okay, sure.
Next, Professor, I did the Durbin-Watson test.
Oh, just plot it, then
Yeah,
explain it.
Oh, So-
Isn't this the one John shows?
Yeah.
So you also show the years. Oh, okay.
So
I
here
didn't notice that.
we can see, Professor, the residual is going. It fluctuates from every year, so we can see that becomes higher
Ah.
going to something.
Yeah. Okay, let me see the other one. All these dots.
The dots.
All these dots. Oh, okay. This is what you shows. Okay, and the one is connect all the dots into the
To the line.
lines. Okay, all right. You understand it, and they say the plot them as a line graph. Okay, all right. So instead of this one, and plot it as a line graph. Okay, then we can see those very clearly, just like what our textbook has. Understand what I'm saying there? Good, very good. Now we understand it, right? Sure. All right, go on.
So next would be the Durbin-Watson test, Professor. So
Mhm.
in this, the interpretation that's used by the Python is somehow like this. So the statistics that will be output by this function would always be between 0 and 4.
Yeah, look at this one. Durbin-Watson statistics will always between 0 and 4. We explained that in class, right?
Yeah.
Yeah, okay, good.
And since it's the closer to the 0 statistic, it's more more evident to be positive serial correlation.
Mm-hmm.
But since now the result of the Durbin-Watson test is 0.38, it's nearer to 0 than even to 1. So we can say that there is evidence of positive serial correlation in this case.
So this is only Durbin-Watson test?
Just Durbin-Watson test.
Okay, so you don't do the officially just like we did, like the critical value approach or p-value approach?
Oh, not yet. So just the
Oh,
Durbin.
not yet. Okay.
I plan to use a different one, Professor, since it becomes a bit more tedious in coding in Python. I'll
Oh.
try to use R next time. A different program.
Well, we do have the Durbin-Watson test
Yeah,
using the Gradle.
yeah, Professor. I try
Yeah,
to
and
compare.
also, if usually you can check with the Durbin-Watson tables, just
Oh.
like we have it in our textbook,
Oh.
the back of our textbook, and it shows the critical values.
Oh, okay.
Therefore, this is what we just say that these two business students, they're using critical value approach and p-value approach. And the critical value approach, we just located our table
Oh,
and
so-
check with the numbers. One is 150 something. The
okay.
other one is 160 something.
Oh, I can
So you
cross-check
can
it.
check that with your test, the statistic, which is
Okay.
0.385
okay.
something.
Okay, Professor.
But I don't know, maybe you can do that in in Python too.
Yeah, I can.
I
do
don't
that.
know. I don't
Yeah,
know.
I can do that.
Yeah.
Ask
Okay.
maybe later.
Sure. Sure. Sure.
Next is the Broish Godfrey, or the Broish one. So the second one is the p-value. This one is the f statistic.
Oh,
the
this is the
test
p-value?
statistic. The second one is the p-value, professor. So this one is very low. So
Excuse me.
yeah.
What is this?
Oh, this is the.
Oh, it's checking with. Okay, LM test.
Oh, this is just the.
Is this
well,
the LM test?
Oh no, just the.
Oh, this is the B. Okay, okay.
The B.
I think we do have that in our e-views. E-views. We do have that. Actually, this one, this one is the LM test.
Oh, it's this.
This one is the LM test. Look at these numbers. Is this pretty close to what we have it? Using observation times n times r square. So this one is the same as LM test. Okay, so you did LM test, and what is this?
But the Python professor specified this is the other LM test.
Ah, okay. This one we say from there are several
LM.
tests.
Mhm.
Okay, this is one of the tests,
Oh.
which is provided by, we call it BG.
Oh, the BG.
It's Bruch Godfrey test. Okay, this is the same one we put a B. Which one test? BP test. You remember that? The BP test in heteroscedasticity
Bruch Pagan.
is the same statistician.
So many
Bruch what? I don't know. Okay, so this is really LM
Oh,
test.
so I compared it with the other LM test by Python, which is this one.
Okay.
So I think the
John
John
did this one.
Yeah, but I think the n lags was 0. That's why the value was n lag is 9. So what happens if we do that? If we get this, but if we add the n lags to 1,
Yeah.
we get the same value almost as the BG test.
Wow, look at this one. Almost, yeah. And you should put the lag 1 here, since we're working with 1 lag. Okay? We're working with 1 lag. Actually, the result, the comparison here is we look at Durbin-Watson's, and since Durbin-Watson is only allowed 1 lag, and this one, if you want to do the comparison of these two results, you can put that lag equal to 1, 2.
Yeah.
But this one you also can check with the lag greater than 1.
Yeah.
Okay? All right. Good.
The other one is the Leong box. Yeah, Leong box, or the LB test, I guess. So this one I
Yeah.
used 1 lag, professor, so almost the same as
Yeah, sure.
BP and LM here.
Yeah.
But in this one we can actually increase the number of lags. By default in Python, I think it does 10 lags.
Oh,
So
okay.
it shows from
Okay.
1 to 10.
Automatically, default, they
Yeah.
just will do the 10 lags.
Yes, professor.
Okay, sure,
So,
sure.
But here we just consider only 1 first for comparison.
Yeah, okay. All right.
Next, professor, is using the general least squares. So I think it's not clear in the Python documentation that the GLS that they're using is not the same that's in eViews.
Yeah. Okay,
So
okay.
since I noticed that it's not using the AR as part
Okay,
of the
okay, there's
coefficients.
there are many different ways.
Yeah. So
Yeah.
what I tried, there is actually another one, is the GLS AR. So this is now trying to fit with other regressive properties.
Okay.
So I tried to also fix heteroscedasticity. I just added HC0.
Mhm.
And this is the result, professor.
Yes.
So a bit different from the original OLS. I believe the error has changed, and also the Z statistic.
But this one, this is the same as OLS, right? So is this the result? Is the same as our Newey West? Look at Newey West.
Here,
This one is different. This two.
yeah, in the
You mean this one?
this one, professor.
You mean this two? Oh, this is a little bit different. Okay, then how about this one? With our
It's
Nui
it's
West, slightly. Then can you find the Nui West in the Python?
I we tried to compute that, professor, but I'm not confident that it's the right computation for the new
Okay.
West. But here's
Well.
what we tried. So here's the constant, the DPI. So this is the one from the original.
Yeah, yeah. So this is original OLS.
Just the GLS, professor.
Oh, it's GLS. Okay.
And I
Well.
did the adjustment to that.
Yeah. Okay. 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 Well, but since this is general GLS models, there's many ways to do it. Okay, and we will show some other ways from the Python program, but actually, if you can use one way, that would be fine.
Yeah.
Okay, it's better to have several other ways among the GLS to do the comparison, but the result is the same. Okay, all right.
So that's it for mine, professor.
Okay.
So which do I prefer? I would prefer if there would be somewhat easier way.
Yeah.
I'll try to, because I found a different way to do the GLS and fixing the serial correlation, professor, but it's not in Python.
It's
So-
not in Python.
So I might try to experiment a bit.
Okay, all right. That's the PhD students. Well, so actually, so far, in Python, you haven't find the Nui West
No.
methods.
Yeah.
Okay, this is popular in business schools. Maybe not in engineering, but it's really popular in business.
Okay.
Okay, all right. Thank you very much. Then, will be the next one, the last one. So let me come back to Rachel. Well, can wait for me just a few minutes. I need to go to the restroom. Okay, just wait for me a few minutes. Okay. Just
Hello.
Okay.
So this is my one. It's almost the same. So
Okay.
at first I tried with Gretel so that I can compare the results with the Python one. So the results were pretty the same, like really the same. And the expected and resulted sign were also the same. Both regressors are significant in the expected direction at the 5% level. it has 3 stars as well. So, these stars are just for significance. And then examine the residuals. This one, I didn't make this in Python. This one is from Gretel. And we can see that there is a correlation here. And then
So you know
next-
how to draw that from Gradle.
Yeah.
Is Gradle,
It's easier.
user friendly?
Yes, it's user
Very
friendly because I
user-friendly.
can see everywhere there. I don't have to type. Just click and then okay, bye-bye.
Okay, and free, right?
Yeah.
It's free. Okay, good.
And then this one for the Durbin-Watson test.
Mm-hmm.
So my null hypothesis is there is no correlation among the residuals, and alternative is the residuals are autocorrelated. This one is from Gretel. So the p-value is very small, and this one is from Python. We can see that it's the same. So the p-value here is closer to 0. That means it is more evident that there is a positive serial correlation. And then for the Lagrange multiplier, wait, where are we? Are the null and alternative hypothesis for Lagrange multiplier test same as Durbin-Watson? Oh, it's not, because the LM test is used to detect if omitted variables have an impact on the regression model. And then the alternative hypothesis there is that there are omitted variables that affect the model, while the null hypothesis for the LM test is that there are no missing variables. And then for the Durbin-Watson test, on the other hand, this one is an analysis to find serial correlation for the regression model. And then this one is the result for the LM test. So the first value here is the test statistic, and the second value is the corresponding p-value.
What's this number from?
Oh, it's from Python.
It's from Python.
Yes.
Okay.
And then since the p-value is less than 0.05, we can reject the null hypothesis. And then the lag here is 1. And then for the L-box test, this one is also from Python. So the hypothesis here is that the residuals are independently distributed. And then for the alternative hypothesis, the residuals are not independently distributed. So they exhibit a serial correlation. And then we can see here that the test statistic is 39 point something, and then the p-value is 2.69, which is really close to 0, so less
So
than
you didn't do-
0.05.
You didn't do the Q test. I mean, autocorrelation functions. Did you do that?
The autocorrelation function?
Yeah, we say that in this assignments for did I say that? For step 2, run the LM test, and I say that added autocorrelation. Did I say that in when you
I
when
thought it's only at
you know,
L-box.
there's a one you did, right, Rachel? Did you do that, or autocorrelations, or which one? which is John?
I
Is
think it's
John do that? Or you? You didn't do that.
Autocorrelation.
Oh, yeah, yes, you did it. I thought either one of you to do it. Just show the one leg. It's Rachel. Step 5. Didn't I say that use the, since I teach the autocorrelation functions, right? So I asked you to do the autocorrelation function in step 2, included, right? That's why Rachel did, because I say so. Did I say so? Otherwise, how do you know you have to do that? I think I say so. I say so. Okay. Step 2, you have to add one more autocorrelation function test, which is Q test.
Oh,
Which is Q
okay.
test. I
Ah.
taught in the class, right? Yes. Yes.
Yeah.
Now I remember, although my memory is just not very good now. Okay? Okay.
Okay. And then.
But actually you are working
did
with
not.
some others.
Mhm.
So, that business students know that there's many ways.
Mm.
There's not only one ways. this is graduate school. This is not elementary one, grade one. For elementary students, we just teach you do this or do that. But in graduate school, you have to learn why do we do this one, and there's so many ways to tackle the problems. There's not only there's always a better way. Okay, all right. So we do see several other ways from the whatever GLM or LM test or
Yeah.
GLS.
Yeah.
Okay, good.
And
Okay.
then this one is the one that I got from Gretel by running GLS.
Yeah, okay.
And the coefficients and the t values are different.
Well,
But,
the
negative
GLS they are using. Okay,
1.5.
okay. Look at this one. This is from Gretel's, right?
Yeah.
There's another way, say Cochrane, Orchid. This is another, popular way. But I think the book. Did they say something about this test?
No.
Well, they didn't say that, but
I cannot
our
even
our
pronounce this
authors recommend, praise Winston, and actually EVUs do that way too. Okay, and this one is also a famous way.
This
Oh,
one is the
no.
default in Gretel.
Cochrane, Orchid. It's this two-person is our famous statistician. Okay, so there's another way show to us. Okay, very good, very good.
So on
okay.
Gretel it's different, but when I tried it on Python, yeah, we're having a problem here. So it's the same. So I think this is not GLS. I think there is a method that is missing. Yeah, I have a missing method because when I try to run it with GLS regression, it's the same with the OLS. So I
Oh,
don't
the
know what
result is same as the OLS you are
yes,
using.
from Python.
from-
So there is something missing. The AR, I think auto regression. Yeah, AR.
Huh?
The one that Dylan presented. AR is missing
AR1
here.
is missing here.
So what this regression is doing is the same as the original least square only.
oh, okay.
Even though the name is GLS. Yeah, so here, yes, but not in all cases because I got different results. That's why. But it shouldn't be identical.
Mm.
Yeah. And then after the GLS transformation, the serial correlations still appear to exist. I said here it was a yes because we don't have a lot of what do you call that one? Grounds to say that we don't have serial correlation that is happening. And then I've tried this one and then it's still the same.
What
the
is this?
results for Durbin Watson, yeah, it still presents autocorrelation. And
Mm.
then I forgot to answer step 7.
Huh?
Yeah.
Oh, you didn't do.
Because I am so, oh my god, I'm studying for technical interviews. I keep on writing math.
I forgot. That's
I
step
don't know.
7.
It's different.
Okay. All right.
Yeah,
Understand
that's
it.
why I forgot. And then
Okay. Okay. All right. Thank you very much. Okay. So I think this assignment is interesting, right? And it really, learns what we have taught. Okay. And since we have some other ways from those students from engineering, and they show what's the Python function provide. Okay. So any questions about chapter 9 about the serial correlation? Any questions? Okay. Next time I'm going to talk about chapter 12. Okay. From the chapter 12, we will introduce many kinds of time series. Okay, we'll start with let's just see some from chapter 12. Okay, since there's still have some minutes left, I would like everybody to see the models first first of all, let's see equation 12.1. Do you see that? You all have ebooks, right? Okay. See chapter 12 and equation 12.1. Okay, this is YT. I think this is the same as before, right? But X, look at XT. Before, we just have XT. But now, we do have XT, XT minus 1, and XT minus 2. Okay? All right? And look at another one. Look at another one. I'll let you see. Okay. 12.3. 12.3 is what we call, we do have xt plus another variable, which is yt minus 1. Did you see that? Before, we don't have anything about yt minus 1. Okay? Now, we do have. So, 12.1 is what we call, did you learn 12.1 before? You learned 12.3. Oh, okay. And usually 12.2 is the stand for the leg of the x variables. Okay? And there's a terms, there's a names for 12.1 and 12.3. Okay, 12.3 is the difference between these two is one with, usually you also can have the leg of the x variable and also the leg of y variables in the model. So 12.1 is just only legs, x legs terms, and 12.3 is y legs terms. But we do have both of them. Okay, since you learned 12.3, how do you express these models? So you didn't really say what kind of models. There's no name on it. Okay, let me also, since we're doing with the chapter 10, right? Let's see. No, chapter 9. I'll let you see. Look at 9.9 in chapter 9. Although it is not y, but look at this one. 9.9 is the one with y variable and the leg of the y, right? And we call this is a zero correlations. Okay? So you will see that 12.3 is what we call the AR 1, if you have the leg of 1. If we do have y, t minus k, then we have ARK. Understand what I'm saying here? Okay? So we'll get to that next week. Okay? So chapter 12 is huge. Although there's not much, it's not, although it's as many, but it's really not enough. So I will add more for the material of chapter 12. Okay, so we'll stay in chapter 12 for some certain times. Okay, because there's a lot to say. Okay, time series model. Okay, so that's for today, and we'll see you next week. Okay, bye-bye.